In this session, we would like to explore this very important building block for us to derive understanding of composite random variables. Composite random variables, at the simplest level, is the sum of two random variables, such as w equals to x plus y. And of course, you can have minus y, but let's just keep things simple first. Why do we need to be very careful about it? Let's not let our mind or our knowledge about calculus algebra play tricks on our understanding here. So to prevent ourselves from thinking astray, let's understand x as a normal distribution. Remember random variables, right? So a normal distribution and y is another spiky normal distribution, let's say. All right. So two distributions, two bell curves are to be added together. And we say, let's say, suppose W is a derived random variable, a composite random variable made up of adding x to y, or y to x, doesn't matter. Okay, so that's what we are starting off with. Now, number one, W is a composite random variable because we didn't measure W directly. We did not use ruler instruments, use time and spend any resource to capture the data directly as a column of data under W. We didn't. All we did was some previous work where we measured X and measured Y, and we obtain certain distribution like a bell curve and a bell curve. All right. And then we wonder what happens to the behavior when we add X to Y. And for simplicity, we call that W. That's the starting point. Okay. Now, why would we want such a X plus Y composite random variable? A simple situation could be that you take MRT from your house to an interchange. And then from the interchange, you take a bus to your university campus or your office. Okay, so that's a two-part journey. And your house stays near to an MRT station. So you walk there and so walking plus taking MRT, right? So that on a daily basis has some spread, sometimes longer, takes longer, sometimes take a little bit shorter, but not much shorter, right? Because you're just walking a bit faster. So there's a sense that is normally distributed. So let's say it's taking 100 minutes, all right, and a standard deviation of 10 minutes. So that normal distribution, and then after that you wait for the bus and you take the bus and you alight. So that journey, that entire journey, let's say it's 30 minutes. So that's a mean of 30, all right, with a standard deviation of let's say 5. Just arbitrary numbers. Just to give you some sense as to why we may occasionally, not occasionally, but frequently like to compose the random variables together. So as you go through your daily commute, you are able to measure your MRT journey time pretty accurately, and then you write down, and then after that you start or reset your timing for accuracy for whatever it is, or maybe you take a break or whatever, then you start to wait for the bus. And so for that you get another measurement, you get another bell curve, let's say. And then you wonder, well, actually what would be the distribution of my entire journey, right? Because that's the total time you take from your home to your campus or your office. So that will be a cause for writing x plus y. Can you see that? All right. So oftentimes we have to do that. Another possibility is companies' revenue, mainly made up of products and services. X is a normal distribution and can be any other distribution. You know, of revenue from products. Y will be the revenue from selling services. And of course, then the company's revenue, maybe quarterly revenue, is a random variable because it fluctuates and is always made up of x plus y, isn't it? Yeah, okay, because it's the sum total of revenues from products and sum total of revenues from services added together. So W then represents the total company quarterly revenue. So as you can see, many occasions where we want to do this. And of course, the relevant department heads will gather their own data. So as the boss, the management, they will see random variable X, the revenues and sales from products, and random variable Y, the products, the revenue sales from selling services. So they will combine them together to get W as another composite random variable. Okay, so what we are here to understand is that when we add a bell curve to a bell curve, what can we say? Okay, so that is what you want to be asking. Now we want to say three things, two of which will be answered here, and the last one will not be answered here. Okay, so what are the three things? One is, what is the expected value of W? What is the mean of W, that is? The other question is, what is the variance of W? You have to always be asking yourself these three questions whenever you see a new composite random variable. The reason is we know the right hand side. We know X and Y very well. We know its mean, its variance. We probably also know its shape, whether it's bell curve, uniform distribution, whatnot. Yeah. And what we don't know is the left hand side, the composed distribution. So we want to ask three questions. What is the mean of W? What is the variance of W? And what is the shape of W? And in short, we say, what is the distribution of W? Okay. It is the first two questions that we'll be able to answer here. The third question is rather, how should we put it? Rather extensive. I mean, it's not really complicated, but it's case by case. Yeah. So the third question involves asking, what's the shape of W? In other words, when we add normal distribution to normal distribution, what do we get? In this case, if X and Y are perfectly normal, that means they follow the bell curve completely and precisely, then yes, then W from, theoretical derivation and all that, and proving it, we know also that W is also normally distributed. But that's not true for many other different combinations. Like, what if X is uniform distribution, a box, and Y is a triangular distribution? What if X is Bernoulli distribution and Y is binomial distribution? What if this, what if that, right? So the shapes are very, very combinatorial, a lot of possibilities. So it's not easy to answer that, except for the common cases like normal plus normal. Yeah, so then we will be able to find proofs and do that rather easily. So that's the third question that we will put aside. It's an important question, but we won't try to answer that here. The first two, however, we'll be able to answer that here. And that's basically these golden formulas that we see here. And in short, it's probably easier just to remember it as the mean of the sum of two random variables is the sum of the means of each of the two random variables. So expected value of W is equal to expected value of X plus expected value of Y. Now, it's quite a common sense, quote and unquote, thing to say that, well, you just add up the averages, right? So here, if I take an average of 100 minutes to travel from home via MRT to the interchange and 30 minutes from the interchange to my office, then on average, right, not minimum, not maximum, then on average, I would take 130 minutes to go from my home to my office. Don't you think? Yeah, that's quite a common sense thing, but you have to prove it when you have distribution. So that's true. So it has been shown that the intuition is true. So I think this part is not so difficult to understand, but let's just know it for a fact that it is true. What is perhaps more interesting is weighted sum of two random variables. So if you have A and B, let's say they are positive, then that means that if I stretch this right? If A is 5, so I magnify it 5 times. Yeah. If A is 5 and B is 3 or 3.2 or any other numbers, if you scale X and Y, what is the expected value of W? Well, you can pull out the constants. So A gets thrown out of the expected operator. So A times the expected value of X plus B times the expected value of Y. That's it. That's the linearity of it. So it's like factoring out the constants. You can't do that, right? Unless you have proven it. And here, let's know it for a fact that you can do that for the average operator, the expected value operator.